Hello, in this video I'm going to talk about acid-catalyzed transesterification. In the previous video I talked about base-catalyzed transesterification, and I decided that didn't have enough mechanistic steps in it, so I brought on the acid-catalyzed version. I apologize for the bright light that you see right there. I am not as good at videography as I am at organic mechanisms. So, all right, so for this reaction, what we're going to do is we're going to look at the same substrate as we had in the previous video, ethyl propionate. Okay, and instead of using sodium hydroxide and methanol, I'm going to use paratoluene sulfonic. I'm going to use methanol and paratoluene sulfonic acid. CH3OH and paratoluene sulfonic acid. Sulfuric acid is probably more common, but it takes me longer to draw it. So I'm trying to cut some corners here. All right, and that's going to make it's going to make that the methylpropionate plus ethanol. Okay, so it's a transesterification. We're trading one ester for another. Interestingly, though, anytime you have an acid-catalyzed version of a reaction, it invariably has more steps because you're adding proton transfers. And it wasn't good enough in the base-catalyzed version to have just a nucleophilic addition and a nucleophile elimination. So I'm adding 4 proton transfers in this mechanism. That'll keep me busy, keep me out of trouble, keep me off the streets of Grand Rapids here, causing problems for people. Okay, anyways, so let's see here. All right, so how's this mechanism going to start? Okay. Now, the reason why the acid-catalyzed version has so many proton transfers is we have a weaker nucleophile, and so we need to, instead of having methoxide, we have methanol, so that's a weaker nucleophile, and so we need to make our electrophile stronger, and we're also going to do a proton transfer to make our leaving group a better leaving group. Okay, so that's how we're going to justify our excessive use of proton transfers here. Okay, so here's my nucleophile. Oops, and it's just going to sit there for a second because that's right, I got to make a better electrophile. Okay, so I'm going to do a proton transfer to do that. All right, proton transfer, and so I make a protonated carbonyl. Anytime, maybe not anytime, but a lot of times when you're doing an acid-catalyzed reaction, maybe it's safe to say anytime, with a carbonyl, you're going to start with a proton transfer. All right, and then we're going to bring in our weak nucleophile. All right, now we've sweetened the deal for it, so it's going to do this nucleophilic addition. All right, and I'm going to have to erase some stuff because I'm going to run out of space here. Okay. All right, so make this initially. Okay, here's our nucleophile that came in. All right, it's in that protonated form. So we want to transfer this proton from here over to our leaving group, and we're going to do that in 2 steps. Okay, so I'm going to do a proton transfer. This methanol is probably a solvent. Okay, so we've got a lot of it sitting around here. So it's going to come in. We're going to do a proton transfer like so. And that gets us to this intermediate. And so this is the halfway point of this reaction. Okay. Proton transfer, nucleophilic addition, proton transfer. Okay. I'm going to keep going around the board here, but I'm going to erase a couple things before I do that. Okay. All right. Remember that this is our leaving group. We need it to leave. Okay, and we're going to do that by protonating it first. I'm going to take my acid. I'm using toxic acid. This could also be sulfuric acid. All right, so I'm going to come over here. I'm going to do a proton transfer there. This is the third proton transfer of the mechanism. Okay, and that gets us to here. Remember, one of my pet peeves is I like to see 2 curved arrows for every proton transfer. That's just kind of a Dr. Furth special. I don't know if other professors prefer that, but that's what I prefer. All right. Feel free to leave your comments below about that. Okay. All right. So I've made a good leaving group. It's going to leave now. Okay. And I call that a nucleophile elimination because I am borrowing from Joel Carty's terminology. I thought great way to think about it, or good enough for me. All right, whoop, that's a plus sign. Okay, we're almost at our methyl ester at this point. Okay, we have one thing left to do, and that's another proton transfer. So I'll use this alcohol, come around here. Proton transfer. Okay, and that gets us to our methyl ester. Okay, so let's review here. This was 6 steps. Each step was 2 arrows, so we're talking 12 arrows. That's a lot of curved arrows, but there's some symmetry to this, like some other mechanisms. The Fischer esterification is pretty similar. Okay, so kind of a summary. 6 steps. 5, 6. Proton transfer. We're making a better electrophile, followed by a nucleophilic addition. Okay, followed by another proton transfer. Takes us halfway through the mechanism. Then we have another proton transfer sandwich, a nucleophile elimination, and then another proton transfer. Okay. This is actually the same mechanism as acid-catalyzed hydrolysis of an ester, only our nucleophile in this case is an alcohol, whereas in an acid-catalyzed hydrolysis of an ester, the nucleophile is water. So we made a little sandwich here. Okay, thanks for watching acid-catalyzed transesterification.